everyone. It's very close to the end of this semester. So let's see the distribution of our quiz. Okay, so you can see actually this is not normal distribution. And actually, it looks like we have two different Gaussian distribution here. Okay, so I guess this is very close to what we get for midterm examination. We have two group of students. The first group of students, maybe they understand well, they study this class comfortably, but we also have the second category of students. They are so struggling in this class, but I hope um, you can survive in this class because I know you are trying your best to do our midterm and final examination. So maybe we already have like 1 or 2 weeks left. So maybe you tell me what I can do to help you to improve your study. Because now we have very clear evidence that we have a second category of students. So in the quiz, you can see the average is 45. So if your score is more than 45, then you already win 50% of the students. And have we announced the answer of the quiz on the course already? Okay. So please follow the question of the quiz because we will select several questions into the final exam. So I hope you can study this questions by yourself by examining the answer. All right, and then for our course schedule, let's see, we will have, all right, so for next week, okay, we will have final examination for Tuesday and Thursday. Okay, so this week will be our last week of teaching. And then for next week, we will have final exam for 1.5 hours Tuesday and Thursday. Okay. Okay, and today we'll continue a little bit discussion about the shortest path problem. And today, before we have seen the example how we apply Dijkstra algorithm to find the shortest path, and today we will go inside the algorithm to see how we can apply this algorithm to help us to complete all the steps of the Dijkstra algorithm. Okay, so I hope you still remember our previous example. When we need to find the shortest path, you need to decide what are these into a step. We already determined shortest path for this vertex in this step. And then set the weight or the distance of each different distances. Okay, so given this example, then we can see the algorithm, Dijkstra algorithm. given a graph G, which is a weighted connected simple graph with all weightings positive. And for this graph G, we have vertices V0, V1 to Vn, and we already assigned the weight of all the edges. Okay, so we call that W of Vi and J. We use Vi and J to define H, and then the weight is called W of Vi J. Okay, and initially we set the weight Wij to infinity if they are not connected, or there is no edges between Wi and Wj, then we can consider the weight is infinity. All right, and then let's see the first step of this algorithm. We have a for loop for all vertices. We have the length of Vi to infinity for V1 to Vn. So only the starting point is 0, A is 0. For the other vertices, initially we set to infinity. And then that particular set S is set to an empty set in the initial step. Alright? And given this, we can jump into a while loop, how we update and how we determine the paths of this graph. Okay, then we consider the condition when the terminate vertex Z is not in the set S. Then we follow this while loop until the terminal vertex already included in this initial set S. Then we jump out of the while loop. Okay, next let's see what will we do in this while loop. Alright, firstly, we need to examine if a vertex is not in S and it with the minimal length LU, then we call this vertex U. Once we discover the vertex with the minimal length, then we include this vertex into this spatial set S. Alright, so remember in our previous example, initially all the weight of the vertex are infinite. We only have the initial vertex which has scale of A equals 0. So we will include the vertex A into our special set S because it has a minimal length. And then we jump into the for loop for all vertices V not in S. Then we consider if LU plus WUV less than LV, then we update the max. Okay. So let's see for all vertices V not in S. In the first step, we already include the initial vertices into our set S. So we need to consider the other vertices. Now they are all infinity of their lengths, right? So next, let's consider if LU plus WUV, whether it's less than LV. Okay, so now we know we have only the initial vertex in the set S. Then we need to consider all edges connecting U to other vertex V. Right? So that will be our iteration 2. So now we have LA in our set, and we connect the edge AB and C because B and C are vertices. They are not in the set S or V. But we need to consider the length of A plus 4. If this is the length of B. So in this case, the length of B is infinity, and 0 plus 4 is less than infinity. If it follows, then we will update the length of V. In this case, we update the length of B. Okay, so maybe we can go back to the algorithm. Alright, so let's see if this position follows, then the length of your V is updated by your U plus WV. In our case, we have 0 plus 4. Then we update the length of vertex B by 4. Okay, so now you can consider all the other vertices not in S. So in this case, we need to consider because of the B, right? So we need to consider C, D, E, F. Okay, so when you consider C, then the length of C is updated by 2. But previously, we didn't consider the D, right? Because D, we don't have H connected to A. But remember, in our algorithm, if we have no H's to A, then we consider the weight A to D, A to D, A to D to infinity. So once the weight is infinity, then it was when you up, it's not likely to satisfy the condition to update its weight. So basically, you don't have to consider all the other vertices. You don't have to consider this vertex for updating there's no edges of those vertices. But in our algorithm, actually, we consider so you don't have to update. All right. So once we have updated all the lengths of the other vertices, then that's the end of the while loop. Okay. Then in next iteration, we consider after we update all these lengths of the vertices, which vertex has the minimal length? Okay. So currently we have lengths from those vertices into the so this gives us the results of next iteration. So in next iteration, we choose the vertex with the length, minimal length, which is C. Okay, so we put C into the so give a circle here. Then you can follow the while loop to complete the algorithm. 我要那个简报笔。Alright, so you will repeat this process until Z is included into the sentence. We can start this algorithm. So we call this the Dijkstra algorithm. Okay, so if you remember what we have discussed in chapter 3, right? We have introduced several different algorithms. So what kind of the Dijkstra algorithm is because it's close to the end of the semester, so let's try to give away more points to you. One is homework. Raise your hand and answer what type of this algorithm is when we study the chapter 3. Okay, very good. Greedy algorithm. This is a greedy algorithm because we are trying to discover the shortest path by each iteration. Because the shortest path among all possible paths. So maybe this path is the shortest among all different possible paths. And we extend one step, one step, one step until we reach the destination. So this is a very standard greedy algorithm. We can make each step the shortest. Then maybe the whole length, the path from A to Z will be minimal. So this is an example of greedy algorithm. Very good. All right. Any question for the algorithm shortest path extra algorithm. Okay, if no problem, then we go to the last section of this chapter, 10.3. We are talking about planar graph. So we will see what is a planar graph and what kind of theorem or formula we can use to determine planar graph. And then we will introduce a very important concept, which is called homeomorphism. Okay, so remember we have introduced isomorphism. Right? So this is another kind of concept, homeomorphism. Okay, the planar graph is, the definition is it is called planar if it can be drawn in the plane without any edges crossing. So we call such drawing a planar representation. Okay, so let's see. This is a very standard K4, complete graph with 4 vertices. So in standard way, we draw K4 this way. But we can draw the planar representation of K4. If you consider, we have talked about the vertices just like the pins on the blackboard. And then we have the rubber band for the edge. So if you draw this edge out of this direction, just like this, this is a rubber band attached by these two pins. If you draw this rubber band out of here, then you can see actually these two graphs are isomorphic graphs. And then we have no edge crossing. And this graph is drawn on the plane. Right? If you consider this one is a plane. So this graph is drawn on a plane without any edge crossing. So we can call this one before is a planar graph. Okay, so now you can try your best to draw its planar representation. If you can draw the representation without any edge crossing, then we can call this is a planar graph. So take Q3 for example. The standard Q3 actually we have a lot of edge crosses, right? But if you consider the first square and the second square, and you make the first square smaller inside the large square, then still we have these four edges connecting both square and large square. Then we can have a planar representation of Q3. So in this planar representation, you can see actually we have no edge crosses. And this one is so once you can draw the planar representation, then we can call Q3 is a planar graph. Right? So what is the previous example of a very famous problem or very famous graph is also a planar graph? One extra point. Maybe in 10.4 or 10.5. That's the first planar representation we have seen in this chapter. But we didn't talk about any properties of planar graph yet. But that will be the first planar graph. If you remember, there is a ball, and we push the ball onto the surface of the desk to make it planar. What is that graph? Or what type of problem it is? All right, I will switch to that slide slowly. And during this process, you can still raise your hand to give your answer. Then you can get one extra point. All right. Anyone? Planar representation. She goes first. the wheel actually already open because this is no function so what was your 7 3 I talking about 7 3 actually you can see the right place. Okay. So let's see. Where it is. Okay. So actually we have seen the example of Hamilton problem, right? So you can see the original Hamilton problem is a wooden wall with 12 pentagons as its surface. So if you consider this graph, actually we have a lot of inequalities, right? But you can press this wooden ball onto the surface to make it a regular representation. So that we already mentioned, you have the first pentagon and you have the pentagon which is close to next. And then you can make the first pentagon the largest pentagon. And then you press the wooden ball onto the surface of the next to make it a planar representation. Okay, so this one is the first planar representation we have seen in this chapter. So we call this icosis puzzle. Okay, very good. All right. So next, let's try if we can determine if K33 is a planar graph or not. Okay. So you can see the definition of K33 is a planar graph. So we have the first group, and we have each connecting first group and second group. So this is so if you consider the vertex A, B, okay, so we have seen this example, right? Because if you switch the position of E and B, then you can have the vertices H just like our table. Okay, so actually you can discover a path or system of length 4 in K33. Okay, so now you can see we have no edge processing when we consider all vertices A, B, and all its edges. So one type of subgraph of this one to this one. One extra point, what's the name of this subgraph? Please speak a little bit louder. C4. No, it's not the name of subgraph. Because the definition for subgraph is we can arbitrarily choose vertex in the number of edges. Okay, very good. So this is called induced subgraph. Because once you have choose the vertex, then you must choose the edges connecting AB. Okay, so this is the example of induced subgraph. And then next we can consider, because we already have two other vertices in F, so we need to consider where to put F to make a planar representation. So by this graph, we can consider C can be put in two different regions. The first region is called R1, the second region is called R2. Actually, we can consider the region out of this rectangle and the region inside this we have only two different choices. We can put C in the region R1 or R2. So let's try. If we put C inside this rectangle in the region of R2, and then we add all edges connected to A, B, E, then we have the edges C and CE. Now we can say it's safe because once we add the vertex C and all edges, then it's still a paragraph. But in this case, we separate the region R2 into two different regions. So we call these two regions R21 and R22. Right? Now we have only one vertex left F. So let's see what happens if we put F in the region 21. Okay, so F connect to A, B, C. So once you put F here, then connect to A, connect to C. But when F connect to B, we produce H pulses. So F cannot put in R21. So there's R22. Let's see, how about R1? If F is in R1, then it can connect to B and A without H pulses. But when we need to connect to C, then there is absolutely when F is connected. Okay, so in this case, you can see we have tried every way we can do, but we cannot avoid H process. So K33 is not a planar graph. All right, next we will see several theorems to help us to determine if a given graph is planar or not. You don't have to try in our previous slides. Okay, so let's see. The first thing is Euler formula. Okay, let G is a connected planar single graph with E edges and V vertices, and then we can define R is the number of regions in the planar representation, just like our previous example. In this case, we have two regions for this graph. In this graph, we have three regions. So we call the number of regions of this graph is R, and the formula tells us R equals C minus B plus 2. Okay, so this is called Euler formula. Let's see. We have a connected simple graph. This is of degree 3. And how many regions of the planar representation? Okay, so we can apply Euler formula directly. We have 20 vertices, so B is 20. And each vertex is degree 3. So hopefully we can apply hand-shaping theorem. The summation of all degree will be 2 times 20. That will be 2 times E. Okay, so 2 times 20 is 60. 60 equals 2 times E. This is hand-shaping process. So the number of H will be 30. Okay, so if the H number is 30 and the vertex is 20, and 30 minus 20 plus 2 will be 12. So in this case, we will have 12 different regions of this planar representation. Okay, next let's see another definition, degree of a region. So when we consider the degree of a region, that is the number of edges on the boundary. Okay, so let's see this graph. We have different regions of this graph. For example, R1, R2, and the region outside this graph R3. So let's consider the degree of regions. What's the number of edges on the boundary? For example, R1 is a triangle. So the number of edges on the boundary is 3. And then we can see when the edge occurs twice on the boundary, then we will count twice or 2 of the number of boundary, number of region. For example, we have 1 edge here. So you need to trace along the boundary and calculate how many edges contribute to the number of the boundary of the region. For example, we can put 1, 2, 3, 4, 5, 6. Okay, so the degree of region R2 is 6. And then when you travel along the boundary of R3, maybe it's 1, 2, 3, 4, 5, 6, 7. Okay, so the degree of region of R3 is 7. So that's the definition of a degree of regions. All right, so let's see the corollary from Euler formula. If G is a connected planar simple graph with E edges and V vertices, and V is larger than or equal to 3, then we will have E less than or equal to 3V minus 6. Okay, so let's see how this corollary can be directly derived from Euler formula. Okay, a very simple observation is actually the degree of each region is at least 3, because we need at least 3 edges to form a region. Okay, so the degree of each region is at least 3. And then the last thing is very similar to the theorem. The sum of the degree of each region actually is twice the number of edges. Okay, so maybe we can see the previous example. So when we calculate the summation over all regions, in this case 3 plus 6 plus 7, that will be the sum of the degree of regions. Actually, the number is equal to 2 times the number of edges. Because you can see, take this for example, when you calculate on 1, then this edge is calculated once. But when you calculate on 2, this edge is calculated twice. So if you add the summation 3 plus 7 plus 6, then the summation of degree of regions actually is just twice of the regions. All right, let's see the proof of the corollary. Why we have such inequality? E is minus 6. Okay, so if we calculate the summation of all degree of regions, then we calculate the summation over all regions. The degree of the regions, we calculate the summation. 3 plus 7 plus 6, that will be the sum of the degree of the region. And we already know it equals 2 times E, very close to HHE theorem. And we know for each region, at least it has 3 different edges. So the length of the degree of the region is at least 3. Once you have R regions, then the summation of the degree of the region is at least 3 times R. So you may have the region of base 4, or you have a number of edges along the boundary 5, 6, and so on. But because the smallest number is 3, so the summation of the degree of the region is larger or equal to 3 times R. Now we have an inequality to connect E and R, because now we have 2E larger or equal to 3R. So we can have the inequality. Actually, 2 divided by 3E is larger than R. If you divide 3 for both sides of this equation. Then we have the Euler formula R equals to minus B plus 2. Then you can replace R actually, if you replace R here by E minus E plus 2, then you will know this value is less than or equal to 2 divided by 3. So after the we will have E minus 6. Right? So we call this the first corollary. We can derive, we can obtain this result directly from Euler's formula. Okay, next one, let's see corollary 2. If G is a connected planar simple graph and G has a vertex of degree not exceeding 5. Okay, so let's see how we prove this. If we have one vertex of degree not exceeding 5, and we prove by contradiction, then we will see, assume we have no vertex exceeding 5. That means all vertices of degree is larger or equal to 6. Okay, so we will use this to derive the computation and how to approve corollary 2. So firstly, let's see, for G is a connected simple graph. If G has one or two vertices, then this result is true. Because when we have only one or two vertices, then we would have one vertex of degree not exceeding 5. Next, let's see the results from corollary 1, because corollary 1 tells us P is a connected simple planar graph, and we have this inequality with V larger or equal to 3. So next, we consider when we have more than 3 vertices, and how we apply this inequality. Okay, so we know now we just consider the vertex at least 3 vertices. So we know corollary 1 holds. So we have E is less than or equal to 3 minus 6. Now we times 2 on both sides. So we have 2 times E is 6E minus 12. Okay, then let's see. When we apply the proof using computation, then we assume the degree of every vertex is at least 6. Okay, so if every vertex of the degree is at least 6, then we can calculate 2E equals to the summation of the degree of vertex V. Okay, and then we know the vertex number is V, and each vertex has degree 6. So 2E, the summation will be 6Z. Okay, and then 2E will larger or equal to 6E. But from corollary 1, we have 2E less than or equal to 6E minus 6. Okay, so you can see these two conditions actually equals to each other. Okay, so now we can see the contradiction comes from we have the assumption every vertex at least degree 6. Okay, then we derive the contradiction to this inequality. This helps to prove that the graph G actually has one vertex of degree not exceeding 5. All right, let's see how we apply this corollary to help us to identify planar graph or not. So let's see. If we need to show that K5 is a non-planar graph using corollary 1, then we can see corollary 1 actually tells us if it is a connected planar graph, then E is less than 3 minus 6. So remember, if P and Q is logically equivalent to not Q and not P, if P follow not Q, then we can claim this graph So let's see how we consider K5 for this inequality. For K5, we have 5 vertices and 10 edges. So we can see each number 10 and vertex 5. So 5 times 3 minus 6, which is 9. So we can see 10 is not listed equal to 9. Therefore, if it does not follow this inequality, that means it is not a planar graph. Okay, this is one way you can prove that a graph is not a planar using corollary 1. But one thing you need to notice is K33, because we have seen K33 is not a planar graph either. But if you use K33, then you will see for K33 we have 6 vertices and 9 edges. So when you calculate this inequality, you will see each number is 9. And 3 times b is 18. 18 minus 6 is 12. Okay, so you can see eventually the number of h9 is less than or equal to 12. This inequality holds. Okay, but one thing you need to notice is K33 is not a planar graph, but it satisfies this inequality. So if you remember the logic, if P and Q, right? So if P and Q does not imply if Q and P, once it follows this inequality, then you claim that graph is a planar graph. No, right? Because we know if P and Q is only notionally equivalent to not P and not Q. It does not equivalent to Q and P. Okay, so this is one thing you need to notice. Do not misuse this of corollary. Let's see. Let's see corollary 3. If a connected planar graph has E edges and V vertices and V larger than 3 and no circuits of length 3. Okay, so this is a very strong condition. It has no circuits of length 3. Then we will have the inequality less than or equal to 2V minus 4. Okay, so let's see. What does that mean? No circuits of length 3. That means maybe the other circuits is 4, 5, 6, but we have no circuits of 3. So that means the summation of the degree of the region is larger or equal to 4 times r. Because for the other circuits, at least the length is 4. Okay, so we multiply the first here, at least 4 times r. Now we have the summation of the region equals to e larger than 4r. Then we will have this inequality e is larger or equal to 2r. Then we can replace r by e minus e plus 2. Then we can derive this inequality. We will have e is less than or equal to 2b minus 4. So if you understand corollary 1 and corollary 2, how we prove the previous corollary, then this one will be very easy. Now we can use corollary 3 to show that K33 is non-planar graph because previously we have seen actually it contains the length at least 4 because when you travel from this vertex 1, 2, 3, 4, right? So for K33, the circuits of the length is at least 4. If the circuit is at least 4, then we can apply corollary 3. Okay, so remember, if it is a planar graph with no surface free, then it will be listed P minus 4. So logically equivalent to not Q and not V. If P is larger than this number, then it is not a planar graph. Okay, so now we can see K3, we have 6 vertices and 9 edges. So E is 9 and 2B minus 4 is 8. So E is not listed or so not Q and not P. That means K33 is not a planar graph. Alright, so we have some tools to help you to identify if a given graph is planar or not. Next, we will see a more strong theorem, Kuratowski theorem. So this theorem tells us a graph is non-planar if and only if it contains a subgraph homeomorphic to K33 or K5. Okay, so intuitively we already know that K33 and K5 is not a planar graph. If any graph has K33 and K5 as its subgraph, then this graph is definitely not a planar graph. Right? But here we have a keyword homomorphic to K33 and K5. So actually it's just not restricted to subgraph. It's applied to a more wide application. Okay. So let's see the theorem. So it tells us if we have K3 and K5 as its homomorphic subgraph, then it's not a planar graph. This is a very strong theorem because we can see and surprisingly, actually, all non-planar graphs must contain subgraphs of K3 and K5. So next, you will see all kinds of examples. If they are not planar graph, then you definitely can discover a K3 or K5 even in that graph. Okay. Next, let's see what is homomorphic graph. Before we introduce homomorphic, we will introduce another operation, which is called elementary subdivision. Okay, so let's see these two examples. If we have G1, then you can see G2, actually we have more vertices along the edge. For example, we have C, and we have another vertex S along the edge. In fact, you can see we have F, G, H, I along the opposite edges. Okay, so actually the operation when you add a vertex along the edge, we call that elementary subdivision. Okay, the formal definition of this operation actually it asks us to remove the edge in C and add a vertex F and then add an edge A and X. So it's not simply like adding a vertex along the edge. It's just remove edge, add new vertex, add new edges. But in the end, they look exactly the same. When you add the vertex along the edges, actually it's results. Okay, so if you put one vertex F here and G here, so now we have G and H along the HBC. So if we actually apply elementary subdivision, what we do is you remove C and add the vertex G and add H, and then you remove the HG and then add the vertex H, and then add H. Okay. So intuitively, you can add vertex directly, but if you want to apply the formal definition of elementary subdivision, you this is arbitrary subdivision. Now we can go to the definition of homeomorphism. Okay, if we have two graphs G1 and G2, we call that homomorphic if they can obtain from the same graph by a sequence of elementary subdivision. Okay, so that will be easy. So we have G1 here and we have G2. So now you can see G2, once you apply elementary subdivision, you can add a vertex S and then add T and then add H and then add I. So you can see actually G2 is a graph applying derived from G1. So we call this two homomorphic graph. Is this clear enough? All right, now let's see how we apply Kuratowski's theorem to determine the given graph G is non-planar. Okay, so let's see, because G is compared to K5, we have two additional edges, and we have 1, 2, 3, 4 additional vertices. But we can see actually G is a subgraph, has a subgraph of H. If we remove these two edges, then H is a subgraph of G, and H is homomorphic to K5, because from H to K5 we have only 4 vertices, additional vertices. Okay, so G has a subgraph H homomorphic to K5. That means we have a K5 hidden in this G. So by Kuratowski's theorem, G is not a planar graph. Now maybe we can go back to the definition of Kuratowski's theorem. A graph is non-planar if and only if it contains a subgraph homomorphic to K5. So in our previous case, G has a subgraph H. H is homomorphic to K5. Therefore, G is non-planar. All right. So you may consider this is very simple because I just told you all non-planar graphs must contain K3 or K5. If you can determine the K5 or K3 in that graph, you can apply Kuratowski's theorem to claim it's a non-planar graph. Okay, so now I will give you one example. This one is a very famous graph, which is called Peterson's graph. So if you want to determine if this graph is planar or not, actually you can reposition its vertex and discover there is a subgraph homomorphic. But in fact, it's not that easy. You can rearrange the vertex, the position, to make it look like and even discover the homomorphic subgraph, which is homomorphic to K3. Next, you will see some homework assignment to help you practice how to determine a non-planar graph. Okay, so we have 4 sections for this chapter. So maybe the deadline, because next week we will have our final examination. So maybe you can hand in your homework assignment by the day we have our final examination. Okay, TA, please help announce this homework assignment. All right. Any question about this chapter or sections? All right. We have very limited time. Because we have chapter 11. So how about next Tuesday we continue to teach chapter 11 and only have final examination on Thursday. Is that better? But you need to prepare more of the course material for your final examination. Yes? Really? Okay. Okay, so please announce the information of final examination next week, Thursday. All right. In chapter 11, we will see a very special graph, which is trees. So you can see, because trees is quite a lot for all kinds of computer science problems. So we will take this particular graph as one chapter, introduce the properties of the trees. All right, in this chapter, we will see tree traversal and what is spanning tree and minimal spanning tree. So let's see the first section. Okay, so we have introduced some definition about trees. Tree is a connected, undirected graph with no simple circuits. Okay, this is very important because for the graph of any circuit, the following example, G1, G2, G3, G4. Actually, G1 connected undirected graph. So G1 for G2, actually A, C, A, F, E, okay, it's also good. And then for G3, so actually these are the circuits, right? A, B, so once we have circuits, it's not true. Then for G4, okay, so it's not a connected graph because C, but you cannot travel C to A, so actually we have two connected components of the graph G4. So G4 is not a tree because we need a connected, undirected simple graph of the graph with no simple circuits. From the definition of trees, actually we can define a forest. A forest is a graph has no simple circuit, but it is not connected. So in this case, this is a graph. So we call this graph a forest because we have more than one connected component. Okay, next let's see a theorem about trees. The undirected graph is a tree if and only if there is a unique simple path between any two of its vertices. Okay, so that means if you can discover a simple path between any two of the vertices, that means this is a connected graph, right? Because every two vertices is a path. And we have important word unique simple path. That means from any two of the vertices, you can find a unique path, but you cannot find two different paths. Because if you have two different paths of these two vertices, let's see how we prove this theorem. So if it is a tree, then let's see how to prove we can have unique paths between any two of the vertices. So and since A is a tree, and by definition of tree, we have no simple vertices. So if x, y are different pair of vertices, then there is a simple path by the theorem 1 of section 4. So let's see what is the theorem. There is a path between every pair of distinct vertices connected on the regular graph. Okay, so this is very intuitive, right? Because given a connected on the regular graph, because it is connected, so you can discover a path between every pair of the vertices. Okay, so if it is a tree is on the right connected graph. So by the theorem 10.4, we can discover a path between every pair. Now we need to prove the path is unique. So it is very easy because once you can discover a second path, the original path is not unique. Then the first path and the second path will form a circuit. So it will not be tree anymore. So we can infer by theorem 10.4, we have a path, and the path must be unique. Otherwise, it will have a circuit in its graph, and it will not be a tree. But we assume the graph is a tree. Okay, let's see another direction. If we have a unique path of any two of the vertices, how to claim this graph is a tree? Okay. So now we can assume there is a unique path between any vertices, and then we can assume, firstly, the graph is connected because we can discover any path along the pair of the vertices of the graph. So the graph must be connected. And then we have no simple circuit because we already know the path is unique of any pair of the vertices. So if it is a unique path, that means there is no circuit in this graph. So we can claim it is connected, it is a graph with no circuits. So by the definition of tree, this graph is a tree. Okay, next, let's see the definition of rooted tree. So previously we have the example G1, G2. We don't know which one is root, but for rooted tree, we have a special name root for that tree. Okay, so if we can assign a vertex a root, then every edge is away from the root, so we call this graph rooted tree. Okay, let's see more terminologies. Okay, for rooted tree, we can define the parent of V. So actually we have parent, we have child, and siblings, and ancestors, and descendant, and leaves, and internal nodes, and subtrees. Okay, so let's see this terminology. Okay, the parent of V is U. There is the age from U to V. So in this tree, once we have age from U to the vertex V, then we call the vertex U is a parent of the vertex V. Okay? Then U is a parent of V, and V is called a child of U. So in this case, we can see Nicholas, we have age connected to Johansson, Nicolaus, and Jacob. So we can see this vertex is the parent of these three vertices. So this vertex is child of vertex in the past from the root to this vertex. So actually, you can travel from the root to any vertex in this tree. Okay. So if the vertex is along the path, when you travel from root to that vertex, so the vertex are called ancestors of that vertex. So take this path for example, we can see when we travel from root to this vertex, we can travel this one to here. So these two are called ancestors of this vertex. Okay, then you can see for this one, it has more ancestors. We travel to this vertex. Actually, we have one, two, three ancestors of that one. Okay, so let's see what is descendant. Descendant of a vertex V are those vertices have V as the so actually you can travel different paths from Nicholas to the unknown. Okay. So if you take Nicholas as ancestor, then these vertices are all its descendants. So actually, in this example, you can see all the other vertices are descendants of Nicholas. And for your head, then we have this vertices. They are all descendant vertices. Alright, next let's see. If we have a vertex of the tree with no children, it's called a leaf. Okay, so actually in this one is a leaf because it has no children. So the leaf with no children, then we call it a leaf node. Otherwise, we call it internal vertex. Take this one for example. This one has children. This one. So this is a leaf. This is internal vertex. Alright, and we already know subtrees. Subtree is also a rooted tree. So this tree is a subtree of Nicholas. This tree is another subtree of Nicholas. It's rooted by Rohan and Nicholas. Alright, so maybe we can use this example to know more about these terminologies. So find the parent of C. So so the parent of C, because we have H or triangle from the root E has H, so E is the parent of root C. And then the children of G. Okay. So G is so G, the children of G is H and J. Okay. Then the siblings of H, siblings means they have the same parent, just like our brothers and sisters. We have the same parents. They are called siblings. So siblings of H actually is I and J, because they have the same parents J. So I and J are siblings of H. And then ancestors of E. Okay, so we can see E. So the ancestors of E is A, B, C. And then the descendant of B, B is here. So its descendant is C, E, E. Okay, you can find all internal vertices or leaves. In this case, the leaves are E, F, K, I, L, M. They are all leaves. The resting vertices are all internal vertices. The subtree root is G. Okay. If we take G as the root, the subtree will be this one. Right? I hope you get familiar with these terminologies because we will discuss more about the properties of tree. All right, that's all for today. I'll see you next time.
有要加分吗？刚刚他说是什么？没有，但我6块1就是哦，开展哦，80分，哎，可以吗？加不能拿走，不能拿走，看那个你说的结果。7吗？8分。我想一下啊。还是，那你们有问题的话，可以在纸上写一写，然后放 个改的菜。都改好了。是箱子是吗？箱子买的是看。我也不知。如果有问题写完，放在另外一个地方。